lecture we mentioned Sobolev spaces, and we mentioned the space H1. Today we will talk about the space H1 or W21 in more details. And this space H1 is a subspace of L2. So it's what functions belongs to H1. We take functions u that are in L2 and such that for them exist weak partial derivatives, and weak partial derivatives are also in L2. And we're talking about L2 of omega, and we will assume that omega is a domain in R1 which is bounded and that has a sufficiently regular boundary, for instance Lipschitz boundary. And I need to comment that if we want to check whether or not function f belongs to H1, we need to check three conditions. We need to check that function is in L2. We need to check or compute partial derivatives where we can that they also in L2, and we need to make sure that weak partial derivatives exist. So here is an example, simple example, illustrating that we shouldn't rush when we're making our conclusion. Say, let's look at this function that equals 0 at the interval from -1 to 0 and equals 1 from 0 to 1, right? So this is a step function, Heaviside function. So if we look at this function, then we see that our function, say u, right, is an L2, right? We can check this condition. And if we think of a derivative, then its derivative equals 0 almost everywhere, right? So we may think, oh, it's also in L2. But because it's almost everywhere 0. But now let's compute the weak derivative. So to compute weak derivative, we will recall formula that has a structure of integration by parts. So if we want to compute u prime, we have to take function phi, test function, so function that is infinitely differentiable with compact support, and here switch the derivative. So now let's start with right hand side, and try to compute it. So I put here minus. We have integral from -1 to 1. From -1 to 0 it is 0, and from 0 to 1 it is 1. So first integral will be 0, second integral it will be function phi evaluated at 0 and 1. At 1, 1 is a boundary point, so our function, since it's has compact support, will be 0, and we will end up with phi at 0. And phi at 0, if we review video 16, can be written in this form where delta here is Dirac's delta function. And so since phi has a compact support, so we can write this integral within our domain from -1 to 1. So basically we have the form that we wanted to get, right? So here is the form, and so we computed that the derivative of our function is Dirac's delta function, and delta function is not function from L2, right? Because if it were in L2, right, delta function equals 0 almost everywhere. If it were in L2, it would be in the same class as 0 function, and then the integral should be 0, right? But we know that integral of delta function over the real line is 1, right? So it's Dirac's delta function is not a function from L2. Okay, so this was an example illustrating the idea that we have to check that U is from L2, has the derivatives exist, and they also from L2, right? So this is a definition. So next, H1 is also an infinitely dimensional linear vector space, right? So what is a vector space? Vector space, of course, you know the definition. It's a space that consists of that has elements, and there are two operations, right? Addition for elements and multiplication by scalars. And this operation, they satisfy a long list, I believe 8 items, 8 axioms that must be satisfied. So it is a vector space. And also H1, since it is function space, right, it is infinitely dimensional space. And in this space, we can introduce inner product in such a way. So inner product in H1 would be inner product in L2 of two functions u and v, and plus the product of their gradients in L2. So here I wrote is using integral notations, the same line. So it will be integral, and here we have uv and inner product of two, or dot product of two gradients. Right, so typically people don't write here, or in some literature you may not see this inner product notation, so it's just written gradient u times gradient v, but this is what it's meant. And using this inner product, we can write the norm of a function, and that would be, of course, this integral u square u times plus magnitude of the gradients squared, and since they must be in L2, so this norm must be so the integral must be convergent, right? So it's less than infinity, right? So this is about inner product and the norm. And the next statement would be that we can put it as a theorem that H1 is a Hilbert space. So since we've already mentioned that it's a vector space, we mentioned inner product, so and the norm, so what we need to prove? We need to prove that this is a complete space, right? So that every Cauchy sequence converges to an element which belongs to H1. And the proof is based on the fact that L2 itself is Hilbert, right? So so how to prove this? We can consider a sequence UK, a Cauchy sequence, and such that each element belongs to our space H1. And then if we take, since this is a Cauchy sequence, right? So if we take two elements with big numbers k and m and consider the norm must go to 0 as km approaches infinity. And here I just wrote the norm using these integral notations. So in this formula we just replace u with uk minus um. So this is the first term, and this would be the second term. And since we know that this goes to 0, I put that this approaches 0 as k and m go to infinity. So what we have, a sum of two non-negative terms goes to 0. That means that each of them goes to 0. So from here follows that this first integral goes to 0, and the second integral, this integral goes to 0. And then from this first line we can say that this is the norm of this element uk of this difference uk minus um in L2. It goes to 0. And if we look at the second integral, so what is the structure? So we have magnitude of a gradient, right? Difference of two gradients. It means that how it's constructed, then it will be sum of differences of partial derivatives, and they all non-negative, so each of them must go to 0. So integrals of this type must go to 0. And what is it? This is just an L2 norm of this difference, and this goes to 0. So here I'm just copying what we had here in the bottom, right? So now we know that norm in L2 of this difference approaches 0, and norm in L2 of derivatives, difference of derivatives also approaches 0. And for each derivative, j here runs from 1 to n. And so these both norms are L2 norms. So now we will use the fact that L2 is a Hilbert space, right? So L2 is complete. So it means that exists functions u and v1, vn in L2 such that this sequence uk approaches u, and each sequence of derivatives, I put here dj, but dj is the same as dx, j, dx, xj. So each of these sequences approaches some elements with j in L2 as k approaches infinity. So now we have n plus 1 convergent sequences, and what is left to show that they are not just functions, but these functions are derivatives of u, so they are all connected. And to show that, we will start with uk. Each element of our sequence uk is from Hilbert space H1. So weak derivatives exist for such functions, so we can write this formula where we can just switch a derivative from phi to u. And then starting with this formula, we will take a limit as k approaches infinity. As k approaches infinity, uk will go to u, and this dxg uk will go to vj. So we will have this formula that shows us that indeed there is a relation between function u and vj, and vj's are weak derivatives. That finishes the proof. So now let's consider an example of a function from the space H1. And so here is the function magnitude of x to the power epsilon. Here epsilon is an arbitrary number, real number, and we consider this function in the unit ball centered at the origin, so our omega will be a unit ball in Rn, and our goal is to find epsilon such that our function u belongs to the space H1, and we will see that even for some negative values of epsilon, function will be in H1, right? So for negative dimensions, it doesn't have to be continuous. And so let's do this. So the plan is we will find epsilon for which u is an L2. We will find where we can compute derivatives that derivatives are in L2, and then we will check existence of weak derivatives. So this is the plan. So first let's find epsilon such that u is an L2. So we will write norm in L2 of our function u, right? So this is our function u, and then this norm, this integral must converge, right? So what we will do to compute this integral, we will switch to spherical coordinates. So by switching to spherical coordinates, we will be able to integrate with respect to r. So right, so this is r from 0 to 1, and with respect to sphere, and then also when we are switching to spherical coordinates, we need to take into account the Jacobian. So the integral can be written as follows. So this term r to the n minus 1 is coming from Jacobian, and then we will integrate over the sphere. So that's omega 1 is surface area of the unit sphere in Rn, and so by integrating we will see that this 2 epsilon plus n must be positive, right, for integral to converge. So we write this, and from this inequality we have this, our first condition: epsilon must be greater than negative m over 2. So now let's recall that when we have when both weak derivative exist and our regular normal derivative exists, they must coincide. So let's compute our derivatives, but we will use the fact that our function has this form. So instead of computing each derivative separately, we will compute this integral. So we will compute the gradient and of this function, and we will show that this integral converges. So then we will have this expression if we replace u with our function, and we want to find epsilon for which this integral converges. So again, we will switch to spherical coordinates, and then gradient, since our function depends on r, only gradient will just result in differentiating with respect to r, and again this term came from the Jacobian by switching to spherical coordinates from Cartesian, and this omega n again is surface area of the unit sphere, and Then after doing this simple computation, right, we differentiate with respect to epsilon, then squared. So epsilon squared appears from here, and here we will have, when we differentiate, it will be epsilon r to the epsilon minus 1, and then squared will multiply by 2 to epsilon minus 2 plus n minus 1. And when we integrate this, we will get this expression that must be that must converge. So from here we conclude that 2 epsilon minus 2 plus n must be positive, and from here we getting just some correction to our inequality. So it must be epsilon must be greater than negative n over 2 plus 1, and so this would be our condition for epsilon. And I have to mention that for instance, if n equals 3 in R3, we will get epsilon greater than negative 1/2. So we can see that still epsilon can be negative. And now let's check existence of weak derivatives, right? So we need to check that this formula holds for any function, test function phi, which is continuous, infinitely differentiable, and has a compact support in our ball. And so this must hold when epsilon satisfies this inequality. So let's start with right hand side. I have copied it here, and then we can notice that so this infinitely differentiable function with compact support, this function from A2, we checked it, right? When epsilon satisfies this inequality, it will be from A2, and then due to absolute continuity of the integral, we can write that it's equal minus limit. And then, so what is the problematic point? Problematic point is the origin. So we cut the origin out. So we will consider a limit when rho goes to 0, and we take our b1 and cut b rho, so small ball. And then we will work with this integral. Okay, so what we are doing, we are starting with the right hand side and want to end up with the left hand side. So we have this limit, and I just copied it here. And so in this limit, so now when we after we cut out the origin, our functions here are smooth, right? So there is no singularity. So we can actually use integration by parts because they're smooth functions. So that's what we are doing. So we're switching our derivatives, a derivative from phi to our function u, and also we will have two integrals over the boundary, right? So here this is our ball b1, original this is our ball b rho, and we will have two spherical surfaces. This would be S1, and this one would be S rho, and nu and n are outward normals for each, and nu j and nj are corresponding components. And so now let's see what happens afterwards when we compute the limit. So our first integral will be approaching this one, right? And that is what we want to obtain. It is here. So it means that we need to show that the rest two integrals will go to zero. The first one is easy to see that it will be zero because we have function phi here and it has a compact support, so on our boundary it will be zero. So the second integral is zero, and the third integral I just copied that. That's what we need to figure out to show that this is also zero. So to do this, first we will estimate the integral. So we write here this integral and we'll estimate it. So the first term, x to the magnitude of x to the epsilon, will end up with rho to the epsilon, since we're integrating over our sphere with radius rho. Then function phi is a smooth function, so it has maximum, so we can just take its maximum, and we will get also, we have to multiply by surface area of our sphere of radius rho, and that would be this surface area of the unit sphere multiplied by rho to the n minus 1. So this and this are constants, so I wrote it as a constant, and rho would be to the power epsilon plus n minus 1. And for our epsilon, we have here inequality. So I just copied it here, and finally we will see that we can estimate everything with the rho to the power n over 2. And when we need to compute the limit, when rho approaches 0, and rho to the n over 2 also will approach 0. So we have shown that this integral also goes to 0, and finally we have shown that this formula indeed holds. This finishes the proof, and I need to make a few minor corrections. So here I forgot the minus sign for integration by parts, so here it is correct. And then if I distribute this minus, then here I will have a minus, and here I will have a minus. Now I hope everything is correct. Thank you.